Hey everyone, and welcome! Today we are cracking the code on spherical coordinates. Now, have you ever tried to describe a point on a globe using a regular x, y, and z grid? It feels clumsy, right? Well, it turns out there's a much more natural, much more elegant system that's tailor-made for it.
So, let's kick things off with a question. You probably remember this equation from a math class somewhere. X squared plus y squared plus z squared equals r squared. It's the classic equation for a sphere. And hey, it works. But is it the best way? Is there a system that's just built for spheres and cones and things that are round? The answer is a huge yes, and that's exactly what we're going to dive into. So this new Mac for space basically throws that rigid X, Y, Z grid right out the window. Instead, it uses just one distance and two angles to find any point. You know, it's kind of like how we give directions on Earth. We don't say go 3,000 miles X and 2,000 miles Y, we use longitude and latitude. Spherical coordinates do the exact same thing for all of 3D space, and they do it with three key players: rho, theta, and phi. Okay, first up is rho. And honestly, this one's the easy one. Rho is just the straight line distance from the very center of our coordinate system, the origin, directly out to whatever point we're talking about. It's basically the radius. And since it's a distance, it can't be negative, so rho is always 0 or more. Simple as that.
All right, next up is theta. Now, if you've ever dealt with polar coordinates, this is going to feel super familiar. Theta is our around angle. It swings horizontally, starting from the positive x-axis and rotating around the z-axis. Just think of it as the longitude of your point. It tells you how far to spin around the equator of your system. And that brings us to our third piece of the puzzle, phi, which is our down angle. This one is measured down from the positive z-axis, which you can think of as the North Pole. Now, you'll notice phi only goes from 0 at the very top, straight down to pi, or 180 degrees, at the bottom. So why not a full circle? Well, think about it. Theta is already taking care of the full 360-degree spin around the middle. By combining theta's full rotation with phi's 180-degree tilt from top to bottom, we can literally point to any spot in 3D space.
Okay, so we've got these two different languages for describing space, the familiar Cartesian and now this new spherical system. So how do we translate between them? Well, we need a toolkit, a sort of Rosetta Stone for coordinates. Let's look at the formulas that build the bridge between these two worlds.
And here they are. This table is your best friend. On the left, you've got the formulas to go from spherical back to Cartesian, x, y, and z. And on the right, you've got the ones to go from Cartesian to spherical. And if you look closely, you'll see it's all just good old-fashioned trigonometry. Sines and cosines are the magic that connects the distance and angles of one system to the straight line axes of the other.
Okay, so looking at a table of formulas is one thing, but to really get it, you have to see them in action. So for this next part, we're going to put this theory to the test. We'll start with some simple shapes and then work our way up to converting specific points and even whole equations.
And right away, you can see just how powerful the system is. Look at this. The equation rho equals 5. What does that mean? It just means all the points that are 5 units away from the origin. Bam! That's a perfect sphere. Compare that to x squared plus y squared plus z squared equals 25. See how clean that is? Or what about phi equals pi over 3? That describes all the points at a fixed angle down from the z-axis. And what shape does that make? A perfect cone. It's just so efficient.
All right, let's ramp up the difficulty just a little bit. We're going to take a specific point given to us in Cartesian coordinates, -1, 1, negative roots 2, and we're going to find its address in our new spherical system. This is where we'll have to break out that conversion toolkit we just saw.
We can break this down into 3 straightforward steps. First, we're going to find rho, that straight line distance, using that Pythagorean-style formula. Next, we'll figure out our down angle, phi, using what we know about z and rho. And finally, we'll find our around angle, theta, using tangent. But there's a little catch we have to watch out for.
Okay, pause. This right here is super, super important. It's the #1 place people trip up. When you calculate tan theta equals y over x, you get -1. Now, your calculator might spit out an answer like negative pi over 4. But wait, that angle is in quadrant 4. You have to look at your original point. Our x is -1 and our y is +1. Where's that on a map? That's quadrant 2. So you need to find the angle in quadrant 2 that has a tangent of -1. So always, always, always check your quadrant.
All right, so when we put it all together and crunch the numbers, this is what we get. Our rho works out to be 2, our phi turns out to be 3 pi over 4, and after we do our quadrant check, our theta is also 3 pi over 4. So there you have it. The Cartesian point -1, 1, negative square root 2 is the exact same location as the spherical point 2, 3 pi over 4, 3 pi over 4. Same place, just a different language to describe it.
Okay, ready for the final boss? We're not just converting a point anymore, we're converting an entire equation. We're going to take this Cartesian equation here, which you might recognize as the equation of a sphere that's been shifted up off the origin, and see just how much simpler it gets in spherical coordinates. The game plan here is pretty straightforward. We're just going to swap out the Cartesian bits for their spherical equivalents. On the left-hand side, we've got x squared plus y squared plus z squared. Well, we know what that is. That's just rho squared. On the right-hand side, we have 4z, and from our toolkit, we know z is rho cos phi. So we make the substitutions, set them equal, and then we simplify. And check this out. After we divide both sides by rho, that clunky Cartesian equation completely collapses into this beautifully simple form. Rho equals 4 times the cosine of phi. I mean, look at that. This right here is the whole point. This is why we do this. This is the payoff. So we've done the math, we've converted points and equations, but let's step back for a second and ask why? Why go through all this trouble to learn a whole new coordinate system? Why does any of this matter? Well, for starters, like we just saw, it makes equations for things like spheres and cones ridiculously simple, but the real magic happens when you get to calculus. If you ever need to calculate the volume of, say, an ice cream cone or a chunk of a planet, spherical coordinates make those integrals so much easier to handle. And it's not just for math class. This stuff is used everywhere, from calculating gravitational fields in physics to building 3D models for movies and video games. So now you have this incredibly powerful tool in your toolkit. You have a new language that can describe the surface of a sphere with beautiful simplicity. But that leads to the next big question, doesn't it? Describing the surface is one thing, but what about everything inside? How do you go from describing the skin of the sphere to measuring its actual volume? Well, that's a story for the next step in calculus. Thanks for watching.